We have everyone in. We had a couple of folks still joining. All right. Welcome back, everyone. Apologies for the delay. We were having some technical difficulties. Start the recording here. So any questions from last lecture or from the assignment, which is due tonight? Just checking for the chat, see if there is anything. There has been some good questions in the forum. Even if you haven't asked the question, it's good that you look at the posts. Some of them are quite useful, I think. All right. Just to let you know, there will be a new assignment posted later today or tomorrow at most, but this assignment is going to be due in 2 weeks from now. Just as a reminder, next week is reading week, so we won't be having lectures. We will still have the office hours, but not the lectures. So you are welcome to stop by the office hours if you have any questions or want to chat something, or you can just use the reading week for reading. So we have a question, how to reach and edit raw binary file into an array? Well, great question. You need to know how the raw binary file is structured. There is no, if we are just talking about plain raw binary data, you need to know which is the underlying structure of the data. Other than that, you can use, you basically will read the data and place in whatever corresponding array it is. But remember, the issue with the raw binary data is there is no metadata associated with it, meaning there is no information about, you know, how the data was laid down. So I think the example I mentioned last class is, unless if you have a million elements in an option in a binary file, then you don't know if they belong to a 10,000 by 10,000 matrix or it belongs to a 1 million one-dimensional array. So you need to know that information a priori. So as far as I can tell, there is no way in raw binary data to basically to know that, unless that you encode, let's say, if you're reading byte by byte and you encode the first 2 bytes with the dimensions, saying, okay, the first byte is the dimension, then the second 2 are the length of the dimensions, kind of like that. But there is a convention. So unless you predefine what is the structure of the data that you are dumping into the raw binary file, there is no easy way to do that. I don't know if that answers your question, C. It's a good question because the end line of this question is moving into the standardized binary data formats like NetCDF or HD5, that it had the ability to incorporate the raw binary data into an additional structure underlying this data. Lucas is asking, how are we supposed to create for loops to write it element by element? Sorry, my chat is moving. Like we did to save files, or no, you can just dump one option, right? Remember, I think we talked a little bit about this in the file IO lecture. Try to minimize the number of operations. So if you do that within the for loop, then you basically are hitting the file system n times, meaning how many elements you have. But you can have just one function dumping the whole data at once, right? These are good questions. About the first part of the assignment, we must cast everything into char before writing it to binary. Right. So for you're asking for saving the data as ASCII. Yes, that's right. Okay, 1 second. I haven't received any feedback on assignment 3 yet. I think, Rances, you can correct me on this. I think we haven't, I don't remember I have received any notifications from Camille that the assignments are posted yet. But
where you think you get penalized twice, then that is by mistake. That shouldn't happen. It happens sometimes by mistake. Just let us know and we'll correct it. Because if you couldn't know that it is wrong, then that was
exactly, yeah, that's
the point of it. Yeah.
that was exactly what I was going to say. If that happened, like for instance, you didn't comment match and because you didn't get the feedback on time, you still didn't comment match, we won't penalize you twice. Okay. So just let us know. Did I miss something? Okay. I think we have more or less. This part of something where we will rewrite binary and reproduce the data. I guess that I wouldn't be practical in general, and it's just a demo. You can think of a demo like a practice for learning how to do it, but you can think about as a testing unit, as a testing routine. We're going to be talking about that after the reading week. But in general, it's good to read data, to learn how to read the raw binary data. I understand the question because I was just saying, okay, it's not usually the way you will do it unless you know the underlying structure of the data. But think about your own code. So for instance, when you're running on supercomputers, one thing that is limited is for how long you can run using the resources available. So with that in mind, what happens is if you have a really long problem to solve that it takes a lot of time, what you need to do is to what we call checkpoint. So at some point you run out of time because you can run up to, let's say, 24 hours. And if in 24 hours your problem is not solved, you need to do a standby, dump the whole content of your data, and then restart your run in a different shop and load that data. So checkpoints, because they are usually thought not to be shared, many people will use just raw binary data. It's a, quick, dirty kind of solution, but it will work for checkpoints. You can still use NetCDF if you wish, but sometimes, checkpoint files, which are basically dumping the whole content of the problem, the whole information that is available on the memory at that point in time, is dumped as raw binary data. And then when you restart your problem, when you start your program to run, it will read that raw binary data. So that is an application that comes to mind. But the other one is testing, right? So you want to be sure that the data is being saved properly, so you can have these routines for reading the data again, comparing to a known solution, for instance, and be sure that the things work properly. All right. Okay, that was a good Q&A. Again, we will keep some time for at the end if you guys have more questions. So let me start with here. Let me start by sharing my screen. We're going to be talking about a fun topic today, I hope. Computer is getting slow today. Let me know if you should be seeing my slides now. If not, please let me know. Oops. Perfect. So the topic for today is ordinary differential equations, and no, this is not a mistake. We are going to be talking about ODEs, not necessarily in the context of math, although we will be talking a little bit about that, but in the context of how to solve them numerically. So we're going to do a very, very general introduction to what ODEs represent and how can they be seen. But then what we're going to see is how to solve them numerically, different techniques. And the most interesting part is how to do this using libraries. And in particular, the libraries that we are going to visit today are the CSL and the Boost library. Boost will come back later in the course for doing unit testing. It's a good bunch of libraries associated to basically C++, so are very C++ driven. And CSL will also come back in other techniques. So again, good set of libraries to keep in mind. So let's talk a little bit about ordinary differential equations. Just a very, very quick recast for everyone. What basically we are talking about with ordinary differential equations, ODE is derivatives with respect to just one variable. We are going to talk about PDEs again after the reading week. But in this case, we can just think about x being the variable, take the derivative with respect to time or any other parameter that characterize the variable, and then this given by a generic function f of x and t. Now, x can be anything, right? It doesn't need to be one-dimensional. It can be that you have x1 and x2. So it can be that you can actually recast this equation right here as x being a vectorial form, and then the vector will have components x1 and x2. And what you can write in separate ways is the derivative of x1 with respect to, let's say, for the sake of making this concrete, with respect to time, being given by a function f1, function of x1, x2, and t, and then the derivative of x2 with respect to t, or the parameter, being a different function that depends on x1 and x2 and the parameter t. Now, whenever we have this kind of problem, what we are looking after is the solutions for x1 and x2 as a function of the parameter t. Now, the other thing that is interesting, and we are going to see, this is a very, very common technique, is what happened when, so far until here, is what we will call ordinary differential equations of first order, because the derivative, the largest derivative that shows in the equations, is the first derivative of the variables with respect to the parameter. Now, we can also attempt to solve differential equations of higher order. So let's take the second order differential equation, d2x dt squared, given by another function. Well, this can be recasted with a change of variables in two differential equations of first order. And this is a very common trick that is usually used in numerics. Most of the time, independently of the order of your differential equation, you end up solving an equivalent system of differential equations of first order. How do you do that? Well, you just define the first, in the case of a second derivative, a second order differential equation, you define the first derivative, dx dt, as a new variable x2. And then what you get is dx2 dt is equal to f of x of t. And then dx1 dt is only x2, where x1 is equal to x. So again, it's a nice trick. It's quite powerful because it allows you to convert order n differential equation into a linear system of n differential equations. So you probably have seen this in other math courses. Again, it's a quick review just to bear that in mind. And of course, this example, of course, can be applied to Newtonian dynamics, right? Newton's force or Newton's law can be recast into this way as well. And we're going to see some examples. By the way, please feel free to ask questions. I think most of you have probably seen this before. If there is any questions about notation, the notation sometimes changes from course to course, field to field. So feel free to ask any questions. I just have here a few examples of differential equations. So I'm touching upon different fields. The locable Terra one is a system that represents predator-prey behaviors, like the amount of prey or predators that may be usually used in ecosystems. It's a very simple system. It's like textbook example of community variations. And again, you have, in this case, two populations given by x and y. So what these equations are measuring is the amount of individuals in one population. It can be a concentration as well. You can imagine whatever you wish, of one species and the other species. And then this is given by a factor that depends on the own species, but is affected by the other species. So x and y, again, are the two species in the population, or the two different populations. And similarly with the other one. Now, what you will see is that there are a few parameters, 4 parameters that control the growth rate and how each population affects each other. So interesting behaviors can emerge by playing with these parameters. This one on this corner, on the upper right corner, I don't think I need much introduction to this other than say it's not probably the usual way you are used to see it. But again, these equations are recasted in this first order notation or representation. Is our old friend, the harmonic oscillator. Usually it goes like 2 derivatives of x plus a constant or minus a constant, x equals 0. You can recombine these equations. Again, if you take the first derivative with respect to time in the first equation, you get second derivative of x with respect to time equal dy dt, but dy dt is nothing else than minus x. So you end up with x2 dots plus x equals 0, which is the usual way setting the constants k and m equal to 1, the usual way of the harmonic oscillator, but again, recasted into this one first order system of linear equations. This is from chemistry, concentration of this of different substances or substrates, in this case 3 different compounds, variation of the concentration with respect to time, and then coupling constants measuring the reactions between the compounds. There are no linear dependencies here, for instance, x squared times y or z squared. But again, it's a system independently of the particular form of f of the right-hand side of the differential equation. Is a system of first-order differential equations for x, y, and z. Finally, a very well-known example as well, the Lorentz system, one of the first systems to describe numerically chaotic behavior. Basically describe different variables in weather. It can be either temperature, pressure, or any other quantity that you decide to measure related to atmospheric quantities. And again, is casted into a first order system of linear differential equations. And relationships which are no linear on the right-hand side of the equation. As I say, this is an interesting system because you can see a chaotic behavior in the sense that a small departure from the initial conditions to solve these equations may give rise to very different patterns in the solutions. Now, because I say that, and because I forgot to mention this earlier, every time that we have a differential equation, we need to have initial conditions to solve these equations. That's either from the practical point of view or even from the mathematical point of view. A particular differential equation is said to not be well solved or well determined the solution unless you have concrete conditions, initial conditions to be solved. This will translate for PDEs, for partial differential equations, to boundary conditions as well. But in the case of the differential equations, because we have just one variable depending on the parameter, is just the initial conditions for the problem. So any questions about this? Again, it's just a few examples. Some of them kind of well known, I would say. All right. So which are the numerical approaches? So, and again, depending on the particular problem, we have learned in different courses in the university probably how to deal with some particular conditions. Like in particular, we know how to solve the harmonic oscillator. We can use techniques like the characteristic equation to determine if there are solutions, that general solutions to the equation. We can find solutions for the homogeneous and non-homogeneous part and combine and generate the space of solutions for the differential equation. But in terms of numerics, how we are going to approach this problem. So let's say that let's consider this generic form for the differential equation. So in this case, xi represents just a given variable, xi, and then the function can be a combination of all the possible x that we have. So x is, as I was saying before, one way to think about this is think of x as a vector, and this is also known as the vectorial form of the system of differential equation. And then you will have a function that gives you for each x the dependency in the parameter t and the other variables that are part of the problem. So one idea will be to evaluate the function at discrete points in time, t0, t1, and so on. We need to specify the initial condition, as I was arguing before, and then we can consider consecutive points may have fixed time steps. For instance, the steps between t0, t1, and so forth, it will be given by a constant h, or it may be adaptive. What it means with adaptive is this difference between consecutive times may change. Now, you may wonder, why is that? Well, think about just in a very geometrical way or visual way. If you are trying to solve for a function that has a very abrupt or a steep way of changing, meaning that the derivative is very high, you may need to have points together getting together more closely. So you may need to have more resolutions in terms of computational techniques. So that's why you may want to adapt the difference between the points. So that's something we're going to see, but we're going to start with the simple one. Just a word of caution here. You may have also heard this term or nomenclature. A STIFOD is one that is hard to solve, meaning that it requires a very small time step which you will think, okay, if I really want a high resolution for any problem, I will take the smallest possible time step. And this can be really, really dangerous. There are different reasons why it's tricky. One of this is that this can lead to instabilities in some algorithms, meaning this is not related to the computer itself, but the methodology that we use to solve it. But then there can be also problems related in how the computer represents the numbers. We haven't, I mentioned this a couple of times because the topic appears in different questions that you guys ask. But there is something called numerical representation of the numerical values that the computer does, and one has to be aware, has to be careful in how the computer handles those values. Bottom line is be aware of that. Don't think that just minimizing or reducing as much as possible the tiny step will fix all the things. Actually, that could lead to problems. It's due to different things. But the other thing is some methods are better suited to deal with this stiffness than others. So it's good to have an idea of what methods are out there and what methods are better suited for one or the other. Of course, you always have to pay the price on how, and some of the methods that can deal with the stiffness usually can be a little bit slower than the other methods. But that's reality, right? No free lunch after all. So let's start with one of the simplest methods, and probably one method that was developed way before computers were even thought about is what we call the Euler method. So let's use the most general case of having this xi over the t to just one single variable. This extrapolates to or can be generalized to multiple variables, but let's just consider the scalar case, dx dt equal to a generic function f that depends on the parameter t and the solution x. So what we are going to do is just use overall frame Taylor expansion, and that's basically it. So the method that is called is known as forward Euler is based on this expression. It says the next value of the function x or the variable x is given by the value of this iteration plus h, where h is the time step, as we were saying before, times the function f evaluated at tn and xn. Where does come from? Well, if you think about this, think about how you will write f of tx in a Taylor expansion. You will take f, you will evaluate t and x at a given point. That will be your first term. Then you are going to take the derivative of f and evaluating the next point and so on. Well, this applies to x. So consider now the solution x of t. So x of t, it will be in a Taylor expansion, it will be given by x of t at t naught plus the derivative of x of t evaluated at t naught times x, times t, sorry. Well, if you do the math, this is nothing else than this expression right here, because the derivative of x of t evaluated at t naught is nothing else than f of tx multiplied by h, which is the delta t. So this is nothing else than Taylor expansion up to first order. So if I do a Taylor expansion for the solution of f of x of t, then and I truncate up to the first order, that is what I get here with some manipulation of the expression, but that's basically it. And this is the explanation right here. I'm talking up in the air, but this is the reason. So if I take x at a given time tm plus h, I could call this t naught if you wish. This will be x of tn plus h times the derivative of x of x dt evaluated at tm plus second order or higher order terms. Now, if I evaluate this dx dt, which is given by the differential equation, is nothing else of f. And that is basically the expression I have here, where here is approx, here is equal because I can consider higher order terms. But if I take this, excuse me, this terms away, I end up with this expression. So if S is a numerical differentiation, right? That's right. You can think about that. Now, one thing to consider, and this is because it's a nice expression, a closed expression, is this order h squared is what we usually refer to the local error. And this is the local error because it's my next time step. So x at tm plus h, where again, h is the time step, is considered the error I have in one time step. Okay. So if you have an interval T1 to T2, in which you want to solve this equation, you may have endpoints given by T2 minus T1, basically the range of the interval, divided by the size of the steps. So that gives you the number of steps. The global error then is this order h squared times how many times a step I have, which end up being of order h. All this to say that this method, although simple and visually helpful to identify, is not very accurate and is not very stable. Okay, but it's the simplest thing we can do to tackle a numerical differential equation. So any questions about this? All right. So what is the issues with stability? Let's take a quick example and let's come back to our old friend, the harmonic oscillator. So this is the question I showed you before. I hope that you believe me. It's a harmonic oscillator casted in a different manner. Let's use the Euler method that we just described. So x at the next time step is x at the previous time step plus the time step multiplied by the function. Okay. So if I'm here starting to mix a little bit of these system differential equations into what is called a matrix or vector representation of the differential equation, where I put now my two solutions in a column vector, then this matrix is formed such that when I multiply this matrix by the vector of solutions in the previous time steps, returns me whatever is on the right-hand side of the equation. So if you multiply this row vector by the column vector, you will get xn of 1 plus h of xn of 2. And thus you can see it by combining these equations that's the solution that you will get. And similarly with the other term. So this is the solution for that the Euler method gives us for these two equations. So xn of x1 of n plus 1 is given by xn of 1 plus h times xn of 2, and xn of 2 and n plus 1 give us xn minus xn of 1 plus xn of 2. So if we plot this, so this is the same solution as I showed you before. If we plot this, we start with a given value for x1 and x2. Basically, what we get here is this sort of a spiral pattern. Now, it turns out that what this is representing is what we call the phase space of the differential equation. What this is representing in some terms is that this equation is not conserving energy in terms of the physics interpretation that you can give to it. And that is not quite true, because the harmonic oscillator in this particular case, in this ideal case, is conservative. So it doesn't basically lose energy. There is no viscosity that allow you to heat and disperse any energy. So actually the orbits in the phase space of the harmonic oscillator should be perfect circles. So what is happening here, and this is very interesting, this is connected with linear systems and dynamic systems, is if you look at the solution proposed by the Euler method, this matrix 1h minus h1 is the one governing the dynamics of the system. And one thing that you can do in linear systems is you can compute the determinant of the system. If you compute the determinant, it gives you 1 plus h squared. And with the determinant, because it's a 2 by 2 matrix, you can get the eigenvalues. So the eigenvalues where you compute in this way, you can convince yourself are given by, so there are two eigenvalues in this case, 1 plus minus IH, where I is the imaginary unit in this case. You can convince that when you take the module, then this quantity is greater than 1, because independently of what the value of h, recall h is the time step, independently of that value, this quantity is always going to be greater than 1. Now, if you remember a little bit of linear systems, what that means in terms of the solution is that it's going to be unstable for any given value of h. Anything of that h is greater than 0, h has to be real in this case, because it's just a time step. It's the distance between two consecutive time steps in our solution. This system is going to be unstable. So there is no way around to escape this using this algorithm, this Euler method. Okay, this is important to be clear. There is some math behind, The reason why I'm arguing this is unstable is that this can be as a linear system. In other words, this can be seen as capital Y, A as a matrix, and or Y prime, if you wish, A and Y again. And then this can be, the solution to this system can be expressed as exponential. And if the exponential or the exponent of the exponential is greater than 1 in absolute value, it means the exponential will diverge, and that's why we are saying that it's unstable. There's a different way to see the problem, but this is the same message. Okay. So I hope that you guys are okay with that, or not okay, are actually not okay with that, or okay with the explanation, but not with the message of this. And let's see how can we fix this. So it will require to modify a little bit, the solution will require to modify a little bit our approach and our attempt to solve this. So we're going to try to solve the same problem, the first derivative of x with respect to t given by a generic function. But our simplest approximation given by the Taylor expansion will have to change something. And what we're going to change in this case is the point where we are evaluating the function f. Before we were just evaluating xn. Now what we're going to do is we're going to evaluate the function at the midpoint between xn and xn plus 1. Okay? If we do that, and again, this is not trivial, this doesn't go directly from there, but I invite you to follow the computation if you wish to try to do the math. If you do that, and we apply this to the harmonic oscillator, what you end up doing is the following, or what the expression that you end up having is, if we substitute the xn plus 1 by this expression, you will end up with a system that is casted in this way. You will have a matrix multiplying the vectors, or the vector of the solution at the next time step, equal to another matrix multiplying the vector of solution at the previous time step. Now, we can basically just multiply by the inverse of this metric in both sides, and then you will get the vector of solutions alone, a matrix M, and then the vector of the solutions at the previous time steps. Now, if you do that, if you just take the inverse of the quantity, multiply that by this other matrix, the eigenvalues that you can compute, this is where things get a little bit nasty, are given by this expression. And now what you can show is you take the absolute value of these eigenvalues, which as you can see has complex quantities, you can show the absolute values is equal to 1. So it means that in this case, the system that we have reached is stable for any value of h. It doesn't depend on the value of h, actually. Now, one thing to bear in mind, I skipped this point, but what you can see here, what you can see in the proposed solution, in the answers that we're giving for this problem, is that this is what is called an implicit formula. Basically, what we are after is x of n plus 1. But as you can notice here, x of n plus 1 is also part of the right-hand side where we need to evaluate this. We're going to see how to deal with this in the implementation side. But one thing to bear in mind is that the implicit method, so this is called an implicit method, implicit midpoint Euler, if you wish, more details. Implicit methods are often more stable and allows to have larger step size. So that's the thing that you win. But the thing that you had to pay is that they are a little bit more involved in the implementation because you have this dependency on the solution that you are trying to solve on the right-hand side of the equation as well. Okay. Now, if we plot this, what we can see now, if we plot the numeric solutions for the phase space of the differential equation, now we see a perfect circle where basically there is no energy dissipation, the energy is preserved, as it should be in the case of the ideal harmonic oscillator. Okay. All right. So I don't want to scare you, but things get a little bit more complicated because, you know, life is not as easy as the harmonic oscillator. Once one of my physics teachers told me, or professors actually at the university told me, well, if you have a problem in physics and you cannot recast it into some form or some shape of a harmonic oscillator, that's a problem you cannot tackle. I'm not sure if that is too true or not, but there is some nice simplicity assumptions there, let's say. But there are definitely more problems that don't fit into that shape. And for dealing with them, we will need to deal with more robust, more involved methods to solve that. One of them is what we call the predictor corrector. And the idea here is that you will try to compute something, then you will measure something, compare and correct. So basically 2 simple steps or 2 simple ideas: computation of new point, correction using that new point. The idea is that you will keep previous values of the solution to do higher order Taylor expansions. That's the heart of these methods, and then use the function in the last point to correct. Now, one thing these methods are sensitive to is what we call catastrophic cancellation. Again, we haven't talked about this, but this is a phenomenon that can occur when you represent numbers in the computer and the numbers get too tiny and uncomparable between them. So if your solutions or your values, actually when the functions are being evaluated, are in the realm of values that are too close to be compared, or that the values get too low, then you need to be aware, you need to be vigilant about this catastrophic cancellation problem when you use very, very short or very small values for the tiny step. One of the most known ones of this family of methods is the Rushkoot algorithm. Basically is refined by using midpoints, and this here represents just the 4th order of the version. So X, we're going to define some auxiliary quantities, and X prime in this case is going to be the attempt for our solution X, meaning the evaluation of the function, and it's going to give even by the combination of these other quantities. So K1, K2, K3, and K4 are the predictors and corrections associated to each of the evaluations. And if you, again, you can follow the math. I will not go there, but you can, there are different references to follow that. You can see where all these terms come from. They basically corrections to the expansion at higher orders in the Taylor expansion or the Taylor series. So it's a little bit more involved to implement, because you need to evaluate the function at different points, to know the solutions at different points, and then to recast the solution and come back and update the values. There are other methods to deal with that. Notice that, let me go back a little bit. Notice that I have been used, for instance, H all over the place. So means in my implementation here on my description or these equations that describe the method, H is a constant, or at least I haven't given you any sense that H may change. However, we argued at the beginning that some problems will benefit from a variable tiny step. The reason is, like, if you have a very tiny H, on the one hand, it's going to be very slow to solve the problem. On the other hand, you may be close to a catastrophic cancellation problem. So having an alternative where H can vary instead of having a fixed value give you a little bit of flexibility to accommodate for problems that run too slow or that they're getting close to a nasty catastrophic cancellation type of problem. The good news is, at least in this course, we are not going to ask you to implement any of these methods. And by the way, these are called adaptive methods, any of these methods from scratch. And instead, we are going to use pre-built solutions in libraries. And the libraries that we're going to talk, as I was mentioning at the beginning, is GSL, the new scientific library, and Boost, which is a very heavily oriented C++ library with a variety of things, not only numerical techniques, but a lot of things. Now, the CSL, I think we talked about this one before. Francis may have mentioned and showed some examples. It's very C oriented. So it will use all objects of the C realm, like structures and pointers, very, 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 very heavy on the C side. Boost is more on the C++ side, so it will be a little bit lighter, but heavily relying on templates, and you will notice that in the coming examples. So I would like to pause for a second because we are running late, but ask you if you guys have any questions before. What we come next is we're going to talk about, see some examples and talk about how to implement things in particular. But if you guys have any questions about this, our hope is that you may have seen this method, that this is not the first time that you heard about that. But if it is, please feel free to ask any questions or anything that is not clear. All right. So let's start by then looking at a very specific example. So instead of having a generic function f here, I'm going to have a very concrete example. This is just a given differential equation that it happens to have a known solution, an analytical solution. Is this one here, x of t equal to the square root of t minus 1 over t, assuming that the initial condition of x at 1 is equal to 0. The differential equation is x dot equal to 3 over 2t squared plus x over 2t. Now, how are we going? So I'm going to show you this equation solved with Boost and CSL. So we're going to start by looking at CSL. So this is a snippet of code that continues in the next slide. Things that we are going to need for CSL to work is the CSL ODE integrator V2 and CSL error numerical observations. So these are the includes for the header files of the library. The first thing we are going to do is define the function f. So this right-hand side here is going to be given by this function f. And notice that it's going to return an integer. So the function f is going to just define an object, define a model in which the other methods defined by the CSL library can operate on. So t is our parameter t. Then you will have y and dy dt, and then a fourth parameter. So usually the way in which you define the right-hand side for the CSL is in this way. So it's very restricted in the position of in which you need to put the argument. So first comes independent variable t, then comes the solution to the differential equation, then comes the differential equation itself, and then a pointer to parameters. So this is when you can have, or you would like to have variables, or in this particular case, it's not useful because it's just one single equation, but if you have multiple equations, you can have variable parameters for each of them. I'm going to show you an example also how to use that. The other thing to notice is these quantities are arrays. So our doubles are arrays, the solution and the y dt. Notice the const also in front of the y. So again, this is something that has to be determined that way, is the way that the CSL library wants. And this is because when you're going to evaluate the derivative, y has to be considered a constant. Next comes the expression of the right-hand side. And apologize here, there is a typo. This should be 2. So it's 2 times t squared. And then the second term is, notice this is the y0. So y will be just y of 0 because there is only one variable in place. And then 2 times over t, the other denominator. And here there should be a 3. So apologize for that. There are a couple of typos here. I thought I fixed that. Maybe I didn't recompile the slides. But that's basically how you define the right-hand side. The other thing to notice is we are not returning the value of the function. We are returning a keyword defined by CSL success. What it means is simply that things went okay, that there wasn't any problem defining that, and that's it. Okay, so that is quite straightforward, quite simple, I would say. Just define a function. The only caveats to consider is the arguments of the function, how had to be defined, and in which positions they had to be. It's very, very restricted on that matter. Okay. What comes next is the main function, where we actually solve for the ODE. So the first thing I'm going to show you here is just some definitions on some parameters applied to the method. So we are going to define, and this, by the way, is going to use an adaptive Runge-Kutta method. So we are going to define a tiny step to start with, something of the order of 10 to the minus 3. And then we are going to define two different quantities related to the precision of the method. So an absolute tolerance and a relative tolerance. Okay. If you set the relative tolerance to 0, it won't be considered, but you can set the relative tolerance and the absolute tolerance. Then we will define an initial time and a final time, and how many points we want to evaluate it between the initial and the final time. For this example, we're going to use the Runge-Kutta-Karp algorithm. So we need these two lines to define basically what method we're going to use to solve. So it comes from, because I'm using, sorry, I may have forgotten that. Yeah, because we are using the CSL or the EB2 system. What we are going to start is by defining the system. The system, what it has is the following. It has the function that we are trying to solve. So that's the right-hand side that we defined before. It has a null pointer. This is in the case that we have higher derivatives. It has the order of the differential equation. And then again, a null pointer that can be used for if there is more than one variable in place. Again, these things will not be null pointers in the other example, but for simplicity's sake, let's consider this case first. The other thing what we are going to define is what we call the driver. So this is what is going to implement the solution itself. So, and here we're going to just use the ODE-EB2 driver allocation for new y's. We are going to pass by reference, in this case, the system. So you can see y is very C-driven. We are passing by reference and using a lot of pointers here. The system of differential equation. We are going to specify what is the method that we want to use. This is Runge-Kutta-Karp. That's a key word for that. And then parameters like where to start, the value of the time step, the absolute tolerance, and the relative tolerance. Okay. So that is preparing the information for GSL to solve or recasting the system and the method for in the GSL language, if you wish. What we're going to set is t to the beginning time. Then y of 1 is going to just be 0. That's the initial condition. And then we are going to iterate in as many points as we have. So the number of points in this case is 100. So we're going to iterate and just evaluate in a regular grid in time the solution. So t of I is going to be the initial time plus basically the delta between the final time step and the initial time step divided by the number of points. Just a way to generate regular points where to evaluate the function. The other thing we're going to do then is apply the driver. So that is what we're doing here. We're going to get a status of that. For applying the driver, we are going to just use the system that we defined, called D in this case. Again, passing by reference the vector of times, or the initial time in this case, the time where we want to evaluate, and the solution to the differential equation. Now, we use the status to see if it was successful or not. If it was not successful, then there may have been an error, and the status will tell you a little bit about that, what kind of error it is, if we hit an instability, something blow up. And if not, we just print out the solution. At a given time t, the solution for y. And then we iterate as many times time points we have. Again, because this is very C-driven, as you may have noticed with SCDF, we need to have a release of the system, in this case, of the driver. So we use the GSL or the IB2 driver free. That's a way to deallocate the resources associated to the driver and the functions. And that is it. That's basically the way to solve this. So you don't need to know the details of the implementations of the algorithm. You may need to understand what is going on there to know that if it is suitable or not for the problem. But the implementation abstracts all these nasty details of all the prediction and corrections and modifying of the time steps. Okay. So this is the GSL example. So what I have next is another example for the GSL that I will be happy to come back. But let me, for the sake of time, let me show you how to solve the same differential equation, but using boost in this case. So this is exactly the same differential equation. But in this case, what we're going to use is boost. So for boost, we need to include, so as I told you, boost has a good number of different tools. It's quite, and it keeps growing. It's quite astonishing how much different tools or techniques are in the boost libraries. But we're going to need two in particular. ODE-int is the one used for solving numerical, for integrating numerically, and then diagnostic information is for basically graphing the errors. One thing that we are going to do, and you will notice the difference with the previous definition, is again define the right-hand side. I have it right in this case. I believe the 3 is still not a 3, so I apologize for that. My representative, it doesn't really change much because it's just a constant there. But the right-hand side is written in a very similar manner to the previous case. There is no CSL return in this case because it's just need the definition of the right-hand side. We use X because it doesn't need to have an array in this case, given as before, and we use the dxdt and the parameter t. So very similar to before. Some nomenclature is different because boost doesn't require all the or doesn't imply all the restrictions that CSL have. So no major surprises there. This part is very similar. We define the parameters for our algorithm, the tolerances, where to begin, where to start, the number of points that we want to use. Now, we are going, as I say, we're going to use from the numeric package, the ODE set. And similar to before, we need to specify what algorithm we are going to use. So we want to compare or do a TED-to-TED comparison between CSL and Boost. So we're going to use the same, the Cash-Carp algorithm. 5-4 is the order, so it's a 4th, 5th method or order method. And we're going to call this the stepper type. So this is what it will allow us to do the tiny step solving. Now we are going to do this in a controlled manner given by the absolute tolerance, the relative tolerance, and the stepper type. So this is what is going to be our stepper. So it's an object actually. So that's where you start to see the very heavy C++ implications of the Boost library. We are going to define again our beginning time, the initial condition, and we're going to create just a very uniform grid for the time. Okay. Now, the thing that you will notice different here, I don't know if I think Francis mentioned this in the first lectures about C++, this try-catch exception protection, if you wish. So what we are trying here is to ask the compiler or the program to do the integration using an adaptive method given by the stepper, the function, the solution, the vector of times, but also the time where you're evaluating and the initial time step. What happened here, if for whatever reason this fails, Boost will generate an exception, and it will give you a handler to that exception. Usually it's referred as E. This is a very common technique. Something similar happens if you are doing Python or R. You have handlers to the exceptions, and you can intercept that exception. And what basically you can do, and this is why we are also including this diagnostic information header, we can get information about or more detailed information about the error that triggered this call by looking at the diagnostic information. Again, this usually happens if the algorithm detects any kind of instability or something blows up, so that things don't just blow in your face. They kind of blow in your face, but in a more controlled manner. If everything goes well, then the try was successful, there is no catch to be done, and then you output the solution, and then you iterate. Now, I want to mention two things. I see the question for Rob. I will take that in a second. So the auto means is the way to define. Remember, this is very heavy in templates, and you can see the templates probably pooping out there. But basically what it means is a way to define an object within the Boost library. So that's what basically allow you to do. One thing I want to emphasize, this may sound, or especially if you have used Boost before to solve numerically, this is not the usual way you will do this problem in Boost. In one way, we did it this way just to mimic the evaluation in a uniform time, in a comparable way to the CSL solution. The CSL solution, let me go back quickly there, is going to evaluate the solution in this uniform grid in time. These are adaptive methods, as we say, and the adaptive method has the advantage and difference that it changes the tiny step as it fits. So you may end up having this evaluated at different values, which may be good. It may be what you need, but in this case, because we want a apple-to-apple comparison to the CSL function, that's what we do. Let me show you very quickly just for comparison sakes, and there are not too many comments here, so it's kind of selling on itself by the simplicity and how short it is. But this is the typical way you will implement this solution using boost. So you will basically call this integrate adaptive function. The main controller is similar to what is happening here with the stepper and this auto definition. But basically, you compose all that in the call to the integrated adapted, and then what you get is the solution, and you can even specify bright C out. So in that way, bright C out in this case is the function. So you can call what to do, a function to specify what to do with the solution. So in this case, you don't need to worry too much about the uniform grid. But if you want to do the comparison point by point, it won't necessarily match the solution with GSL. Okay, just I wanted to disclose this. If you guys allow me a few more minutes, I just want to go very quickly through this other example. This is based from or taken from the GSL documentation site, which I have links at the end, which is, I will strongly recommend to look at them. The main difference here, we're not going to go through all the details because many things are similar, all this part is similar, but the main difference here is two main differences. Number one, in this case, we are indeed having a system of high order differential equations. It means that we actually have a second derivative, but we can cast this into two first order differential equations. And the transformation is here, again, it's very simple. You convince yourself, you take the first derivative here, you get x dot here, and then basically that is it. Y is x dot, so you very quickly recover that, but you split the second order differential equation into two first order differential equations. And that's the way you will need to encode that. So my right hand side now will have f being a vector of two components. Now y1 and y0. Y0 is over x in the case of the expression. And then the parameters can be used for mu. So something we didn't see before, we saw the values themselves, but now you can see how the parameter is given by the value, the argument, or the parameter mu is given by this param function or pointer, if you wish. Okay, and you can have multiple ones. So if I have more than one parameter, I can actually access those. So that's one thing that generalizes. The other thing is, because it's a second order differential equation, now we will need to build the Jacobian. And that's this part here. That's why we also are importing the GSL matrix function. And that's a way to construct that. And the Jacobian is nothing else, as we saw in the case of the harmonic oscillator, is nothing else than writing this in a matricial form such that x dot and y dot can be given by a matrix multiplying the vectors x and y. And if you do that, computation, then you end up with a representation like this. The math, the details are hidden in the math, but basically that's mostly what you want to know about this implementation. The other thing is now you start to populate things. Your system now is defined not only by the right-hand side, meaning the function in this case, but also the Jacobian. Now our function now is a second order differential equation instead of a first order. And then we are pointing to what is the parameter mu from the parameters. And that's basically it. Then you basically do the same steps as before. You determine what is your relative and absolute tolerance. You determine what is your initial time step. You determine what are the initial conditions. We need two now because it's a second order differential equation. And then you iterate, you apply the solver that you want to use. And if things go well, then you output the solution for the system. And that's basically it. You release the memory, and that's all. Okay, just wanted to mention this is slightly different from the previous examples. Just to conclude, as I mentioned, these are really good references. In particular, both of them has a ton of examples and explanations, really well documented libraries, really well used. Now this is starting to be like, if you are going to do your own, solve your own problems, these are the things that you need to start to use right away, because it's the ones that everyone uses and they have been around for a really, really long time. So they are good in terms of performance. They are good in terms of solutions, of the accuracy that you can reach. So it's really, really good. One final comment is that there are very concrete applications where one will use ordinary differential equations, molecular dynamics, which is going to be discussed later in the course in a whole lecture, and M-body simulations are kind of the realm where these things matter. So these are concrete applications for basically being used in real life research, if you wish. So how did the matrix handle the x squared terms for x dot? So let me go back to that. So basically, oh, I see what you mean. So what you need, and that's why, good question, Alexandra. So you see that the matrix has a 4 by 4. So you need to do a second change of variable there. I didn't go into the details, but you can see that the matrix is a 4 by 4 matrix, right? So what basically you do, you end up having another variable. So it will be x, y, z, w, let's say, where z is the x squared. And that's why you have 4 entries in the matrix. It's a 4 by 4 matrix. So it's a kind of trick that you need to do in order to recast the nonlinearity of the system there. Okay. Right. Good question. Any other questions? All right. So I think that's what we have for you today. Again, it's a quite interesting topic. We kind of scratched the surface, and of course we are going to be learning more in the assignment. So assignment is this 5, I believe, or 4. Can't remember right now. But the next assignment, which will be again posted today or tomorrow, the most, is going to be about solving a differential equation, not implementing your methods. We are never going to do that again. We are going to use one of the libraries, probably both libraries, to be honest, GSL and Boost, and most likely ask you guys to profile the performance of the solvers, so we can see how things behave, which library faster, if there is any real difference, and yeah, hopefully it will be useful for your own projects. All right. We will have office hours tomorrow, as usual. That's also next week, which is reading week, but we will not have lectures on reading week. So we will see you for the lectures in not next week, but week after. Right? And probably some of you, we will see you tomorrow.